back with more rate examples, more charts to make. So in your notes, we're still on page 33. If you will go back up and look, I did want to point something out. We did example 6 on the last video, and this is exactly like number 1 on your practice sheet. And number 8 that we did is exactly like number 4. So these are going to be good examples for you to use when you're filling out your practice sheet. I think I have the correct number 7 for you now. My last video was from an old document. I went ahead and wrote this out instead of trying to write as I go because my writing has been so bad. So let's see if maybe this works as well. I want you to read the problem. If you need to pause the video to read it a couple times, do that. And so I'm going to assume now that you know what the problem says. This guy's trying to develop a new trail mix. He's going to put some chocolate covered peanuts in there, and he wants to add some granola bites, and he gives you the price of each one of those individually, and his total mixture that he ends up with, he wants to price at $3 per pound. So the question is, he's going to use 10 pounds of granola. He wants to know how many pounds of chocolate covered peanuts at $5 a pound should he put in there to get a $3 per pound mixture. So we draw our chart as normal. We've got our players, the peanuts and the granola. This rate, the rate column is going to be, that's a dollar sign, how much per pound. So we know both of these. We know that the peanuts are $5 a pound. There's that info. And the granola bits or bites are worth $2 a pound. And we know that our total mixture needs to be $3 a pound. So that's all straightforward. And now we're going to go put in the second column, which is the amount. And this is how many pounds of each one of these things do you have, or are you going to end up with? So we know we have 10 pounds of granola on the back end. We don't know how much peanuts to put in, so that's going to be our variable. Let X equal the number of peanuts to add. And we know that our final product is going to be those 10 pounds plus however many pounds of peanuts we decide to put in there. So that's how we're going to put that expression in that column. We're going to multiply straight across the rate, how much it is per pound, times how many pounds you have is going to give you the total amount. So 5 times X is 5X, 2 pounds or $2 for 10 pounds of granola is $20. And our final mixture is going to be 3 pounds it's going to be $3 per pound of some amount of pounds, 10 plus however many peanuts we add. So that's the expression for the total dollar amount of our final product. So the equation sets up here. When you're thinking about how am I going to get an equation out of that, you're going to think, well, the peanuts plus the granola have to equal the total. So the amount we charge for the peanuts plus the $20 that we've already determined that the granola would cost needs to equal our total mixture, which is 10 plus X, and we're charging $3 a pound for that mixture. So this one sets up with addition, and now you distribute, collect your like terms, get your X's on one side of the equal sign or the other, solve, 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 and you end up with X equaling 5. Remember that X was the amount of peanuts. That's the question that they asked. How many pounds of peanuts do we have to add to get this mixture? And so that is our final answer, 5 pounds of peanuts. Okay, let's move on to the next page. And I've done one, I've done this one as well before you guys came to the video. So this is one that uses a formula, distance equals rate times time. I don't know if you've used that in math before, possibly in science. This is a really common formula, kind of like area and perimeter. Distance equals rate times time. So this particular problem is going to use that formula, and I'm going to use a chart, but first of all, I just wanted to draw a picture. I want you guys to read it, and then I want to explain my picture. So if you need to pause the video and read it a couple times, do that, and then check back in. So you got a car and a truck passing each other. They're going in opposite directions. And at some point in time, right here, they pass each other. So at this point, we don't really care about the distance the car has traveled up to that point, and we don't really care about the distance that the truck has traveled up to that point. What we're talking about now is the distance that they're now traveling after they pass each other. And the problem is asking you, how long will it take from this moment right here for them to be 190 miles apart? Now, they're obviously not going the same speed. So one is going to be a little further along than the other one. The car is going faster. So obviously he's going to cover a little bit more distance than the truck. But basically, we want to know when this distance, this guy right here, plus this guy right here, when does that equal 190? So we're going to set up our chart. We've got the car and the truck. Our rate is going to go in this column, and it's miles per hour, and that's straightforward. The truck's going 40 miles per hour, the car 55. Rate times time. This column is going to be how many hours are they traveling. So we don't know that, but it's going to be the same for both, because once they're 190 miles apart, that we're going to stop this problem, and they've both been gone for the same amount of time. They've just covered different distances. So the distance that the truck is going to have gone in X hours is 40X. The car, a little bit further, 55X. And when we add the two together, that needs to equal the 190 miles that we're looking for. You solve, and you end up with X equaling 2, and the unit is hours. So your answer is in 2 hours, after they meet, after this point right here, they're going to be 195 miles apart. So I hope that helped. I'm going to stop now. That was a couple, and I probably will do a couple more on another video, but this at least gives you a chance to look at 2 more examples. Thank you.